Welcome to 3 o'clock talk at, it's my accent, talk, at DEF CON. It's going to be Gabriel, Ryan talking about owning land. Let's give him a big DEF CON welcome. Come on. I can't hear you. Louder.
Thanks. You guys awake yet? Fair enough. All right. Got 45 minutes, so like the first 10 minutes of this is going to be really fast. What if I can back up from this thing? Can you guys still hear me if I do this? No? Okay. All right, so I work for a company called Digital Silence. We're a pen testing firm in Denver. I'd talk more, but I'm going to skip that. So my name is Gabriel Ryan, also known in some circles as Solstice. I'm a co-founder, senior security assessment manager at Digital Silence. Used to work for a company called Gotham Digital Science. Before that, I worked for a DoD contractor in Virginia called OG Systems, which between the two of those companies, it's pretty much the best two names in security ever. Like OG Systems, that's fucking awesome. About me, I'm a red teamer, researcher, new dad, interestingly enough. Hence the dark circles under my eyes. My LinkedIn handle is kind of interesting. It's ms08067. Got some chuckles out of you. So this is a talk about bypassing reticular port security technology. So before we get started, we kind of have to go over some introductory information about 802.1x. 802.1x is an authentication protocol that's designed to provide rudimentary authentication to local area networks and also wireless local area networks. The protocol defines an exchange between three parties: the supplicant, which is the client device that you're going to try to connect to the network; the authenticator, which is the network device that the supplicant is connecting to and providing access to the LAN; and the authentication server, which is a host running deeper inside the network, and it's usually running some kind of like AAA software like Radius that actually performs the actual validation. So you can think of the authenticator, the authenticator is going to be like your switch, right, that the device is connecting to. And you can think of it as a gatekeeper, like a security guard. The supplicant's going to connect to it and provide the authenticator with some credentials. And the authenticator doesn't really know what to do with these credentials, so it just forwards them off to the authentication server, which then validates the credentials and then either sends a message back to the authenticator and tells it to either allow this device to access the network or not to. 802.1x is typically a four-step process, beginning with initialization, initiation, then we go to EAP negotiation and authentication. We'll talk more about that in a second. So when we connect to a switch port that is protected by 802.1x, it's going to have it's going to be in one of two states. It's going to be authorized, and when it's in the authorized state, traffic is going to be completely unrestricted, at least by 802.1x, and when it's in the unauthorized state, traffic is restricted to only 802.1x traffic. You mentioned the first step of the 802.1x authentication process is on initialization, and what this means is that the supplicant's going to connect to the switch port, the device is going to connect to the switch port, and it's going to start out disabled. The authenticator is going to detect this new connection, enable the switch port, but the switch port is going to start out in an unauthorized state because we haven't authenticated yet. Then we move to step 2, which is initiation, which we're initiating the authentication process. The first step of initiation is actually optional, and this has security implications that we're going to talk about later. The supplicant it's going to begin with the supplicant sending an ePUL start frame to the authenticator. The authenticator is going to receive this and respond with an EAP request identity frame that just gets sent back to the supplicant. And at that point, that EAP request identity frame is basically asking, who are you? And the supplicant's going to respond with an EAP response identity frame, which contains the username or an identifier such as the username. The authenticator is going to encapsulate that EAP response identity in a radius access request frame because it can't actually validate the stuff itself, and it's going to forward it off to the authentication server, and then we're going to move from step 2 to step 3, which is EAP negotiation. So 802.1x actually implements authentication using EAP, and EAP, you can think of it as like an API or black box for performing authentication. There's many ways to implement it, but the important part is that there's going to be a set of inputs, kind of like a generic set of acceptable inputs that you can put into it, and you're going to get a consistent output from it, which is either an EAP success or EAP failure, or authentication success or authentication failure. So in step 3, what's going to happen is that the authentication server and the supplicant are going to haggle for a bit until they decide on an EAP method they're both comfortable with. When they do, we move to step 4, which is authentication. So this is where we actually perform the EAP authentication. The specific details, as we mentioned, of how this should work are dependent on the EAP method. EAP method is just a fancy way of saying, however you're choosing to implement EAP. But it's dependent on the EAP method chosen between the authentication server and the supplicant. So this will always result in an EAP success or EAP failure message. That's the important part to remember about this. And if we get an EAP success, the port's going to be set to an authorized state and communication is going to be allowed through that port. Otherwise, it's going to either remain unauthorized, or in a lot of cases, they're actually just going to shut down the port entirely and go alert someone, which is bad, if you're an attacker, that is. So we've been talking a lot about EAP. EAP is short for Extensible Authentication Protocol. Really, like calling it a protocol is like not, or authentication protocol is kind of misleading. It's more of an authentication framework because it's only defining message formats. The actual implementation is wrapped up in what's called an EAP method. And as we mentioned, earlier, it's pretty much more like a black box for performing authentication. Just going to briefly mention some notable EAP methods. We're going to talk about them in more detail later, but I should probably hit play on that. The first of which is EAP MD5. Spoiler alert, it's kind of bad. There are a lot of security issues with it. EAP PEEP, another EAP method. It also sucks. I know it's soap, but it looks delicious, so I just wanted to include it in this presentation. There's also EAP TLS, and the traditional school of thought has been that EAP TLS is a lot better than the other two I just mentioned, but more on that later too. With that out of the way, let's do a brief history of wired port security, also just to kind of get ourselves up to speed with what we're going to talk about today. In 2001, IEEE released 802.1x 2001, and this standard was created to provide a rudimentary authentication mechanism for local area networks. The standard was revised in 2004 with 802.1x 2004, and this extension basically was designed to facilitate the use of 802.1x in wireless environments. A year after that happened, a researcher named Steve Riley figured out that you could actually bypass 802.1x 2004 and 2001 as well by inserting a hub between the supplicant and the authenticator. And basically doing this lets you just passively sniff traffic between those two entities, right? You could also interact with the network to a limited degree by injecting UDP traffics. Injecting TCP packets would cause a race condition, so that wasn't really feasible. But this was like the first, kind of documented mention of such a bypass. Fast forward 6 years to 2011, Admiral Security created a tool called Marvin. Marvin was able to bypass 802.1x by introducing the rogue device directly between the supplicant and the switch. So before we were using a hub, which by 2011, those were starting to become harder and harder to find. But ABSTOOL was actually able to, it had two network interfaces. You have this rogue device that's inserted between the switch and like this authorized workstation. And this rogue device has two network interfaces. One of them is connected to the workstation, one of them is connected to the switch, and it actually is able to use a Linux bridge, just kind of forward these packets transparently back and forth, and bypass port security without using a hub. And also, you're able to get full full interaction with the network using packet injection. Later that year, and this is actually probably the most widely used 802.1x 2004 bypass out there, Alva Duckwall introduced a similar bypass technique. It was a little simpler, which is a really good thing. So Alva Duckwall's implementation also uses a transparent bridge to introduce the rogue device between the supplicant and switch. But unlike ABS technique, it doesn't rely on packet injection. Instead, you interact with the network by creating a source NAT using IP tables, and this lets you basically push packets onto the network and make it look as if it's coming from the supplicant device, the authorized workstation, that you're kind of like doing this process. And actually very recently, 2017, we have Valerian Legrand. He created a tool called Fenrir, and it works very similarly to Duckwall's tool, but it's all implemented in Python at a very high level, so you don't run into some of the kernel patching issues that Duckwall's tool is kind of affected by. And it's pretty cool. It has a modular design, support for responder, all that good stuff. So I guess when I started working on this project, it made sense that the first thing to do should be to kind of try to recreate the classic, Duckwall's classic 802.1x 2004 bypass, and also see if there's any ways that it can be improved upon. So looking at Duckwall's 802.1x bypass more closely, we mentioned it used a transparent bridge to silently introduce the rogue device between the supplicant and authenticator, and you achieve network interaction using source NAT. Another interesting feature of Duckwall's device, remember that when we're performing this style of attack, presumably we're not able, this is going to be performed on a network and in a physical environment, like a building or something like that, that we do not own and we're not supposed to be getting into in the first place. So it's not like, you're on like a red team or physical security assessment where you can go walk in, set up this device, install like a monitor and just sit there on the computer interacting with this thing. You have to kind of like get in there, hook this thing up and get out. So it's important when you're doing this kind of thing that however you implement these kinds of attacks, you provide yourself with a mechanism of reconnecting with this rogue device remotely once you perform the bypass and once you've actually made your egress from the building. So the way Duckwall's implementation does this, well, it actually uses two methods. The first is a hidden SSH service that's created using destination NATing, and also it has support for like an outbound like SSH channel that goes through the target network and lets you connect that way. So I was able to improve upon Duckwell's implementation in a couple ways. Back when Duckwell's implementation was first created, the Linux kernel was not forwarding equal packets over bridge. It was completely disabled and as a security feature. And actually, traditionally, if you look at most tools that deal with 802.1x 2004, or bypassing it, should I say, they deal with this problem in the same way that Duckwell had to, which is essentially patching the Linux kernel. The exception to this is Fender by Valerian Legrand, and he just does this completely at a high level using Scapy, so it doesn't really matter. You don't have to rely on the kernel patching. So this made sense at the time, but there are some problems with both of these approaches. And one is that relying on kernel patches can become unwieldy. At this time, there are no longer any publicly available kernel patches for modern kernel versions that will perform this equal bridging. And the reason for that, if you think about what it takes to maintain a tool of any kind, you constantly have to maintain this kernel patch, because if you don't, you can bet that the kernel development team is going to keep working on, pushing updates to the kernel, and kind of if you think of here's your patch, and here's the direction that the kernel's going, and eventually that patch is no longer going to work after subsequent iterations of updates to the kernel. And that's kind of the state we're in now. And then if you deal with high-level tools such as Scapy, they work really well because you don't have to rely on kernel patches, but also it can slow down your bridge under heavy loads because it just isn't able to handle it in the same way that the lower level implementation can. So fortunately, the situation has dramatically improved since Duckwell's contribution. In 2012, equal bridging actually was added to the kernel, but kind of as like an optional feature that you had to enable using the pros file system. The pros file system is pretty cool. It's actually like an API to the Linux kernel that could let you reconfigure stuff on the fly, and you can just interact with it by setting values in files and stuff like that. So basically, you change the value of this file within the pros file system, and you can forward equal packets. So we added that in there. And the other improvement that we added was support for side channel interaction. When Duckwell created his original 802.1x bypass, this was 2011. Cellular modems were pretty unsophisticated. They were slow. They were very expensive. You couldn't just go down to Best Buy or whatever and buy yourself like a $15 LTE modem with a prepaid plan that you could plug into your rogue device. So this is why he kind of had to rely on the hidden SSH service and the outbound SSH channels. This is not a perfect solution though, because it relies on the assumption that egress filtering can be bypassed. So if we can improve upon it, that would be great. Also relies on pushing traffic through the target network, creating an opportunity for detection. Kind of now that we have the opportunity, it's several years later at this point, so we have the opportunity to leverage a lot of this newer cellular technology to kind of establish a side channel to our leave behind device. That also lets us deal with air gap networks and stuff like that. The updated implementation, it actually relies on a side channel interface to provide the attacker with connectivity rather than the hidden SSH service or the outbound SSH channel. We had to modify some firewall rules to get this to work, but it's totally worth it because now you can just connect over LTE. So here's the demo of our improved implementation here to figure out how to get this to play. Oh, cool. Okay. Can I fast forward? Interesting. All right, well. All right, the video's running. I just don't know how to, oh, jeez. Okay, all right, that seems to be working, so I'm not going to touch it. Okay, so, no, it's paused. Okay, so what's happening here, right? In the left-hand side, we have the attacker's device. On the top right here, if you can see my mouse. Can you guys see my mouse? Okay, well, pretend there's a mouse pointing at the top right of the screen. That's the supplicant. Let's play pretend. In the bottom right, that's the switch we're connecting to. You notice that we've disconnected the device here, and we're running this software on the left, which is setting up the transparent bridge we were talking about. And up, it's turning yellow in the bottom right, so that means it's re-authenticating, and we're just kind of forwarding that authentication. And oh, magically the supplicant that's in the top right is able to communicate with, it's going to go back to pinging 8.8.8.8, which apparently this is just what this workstation is used for. Yeah, so now we're going to add network interaction by running this other command. Basically, you can see all these other flags and other information that we're passing to it. When we set up the initial transparent bypass, we were put in a position where you can sniff all of that, which is pretty neat. It's still running? Well, long story short, you can scan things with Nmap, but just I'll post the videos on the accompanying blog post after this, so you can go check them out there. Anyways, so all traditional 802.1x bypasses, either hub-based, injection, or bridge-based, take advantage of the same fundamental security issues that affect 802.1x 2004. The protocol does not provide encryption, and the protocol does not support authentication on a packet-by-packet basis, and that's why this bridge-based bypass works. So to kind of mitigate this problem, another revision to the protocol is introduced called 802.1x 2010, and 802.1x 2010 uses MacSEC, which provides layer 2 encryption performed on a hop-by-hop basis and packet-by-packet integrity checks. So this kind of throws a wrench in the whole bridge-based attack scenario that we just talked about. Interestingly enough, it also allows network administrators with the means to inspect data in transit. So because the encryption is only performed on a hop-by-hop basis, you can still inspect traffic, which is actually a pretty big deal. So 802.1x 2010 works in 3 stages. The first stage is authentication and master key distribution, the second stage is session key agreement, and the third stage is the session secure stage. So stage 1, we mentioned, is authentication. I mean, that's pretty much just the 802.1x authentication process that we talked about before. You're going to perform those 4 steps that we talked about, and then you're going to perform EAP authentication using some EAP method that is going to be selected between the supplicant and the authentication server. And if that succeeds, we'll move to stage 2, which is the session key agreement. Basically, what's happening in the session key agreement is that the authenticator is going to establish that the supplicant is actually capable of supporting MacSEC, and if it is, you're going to install the SAC on the supplicant, and we're going to move to step 3. And step 3 is session secure. So in session secure, basically at this point, everything's encrypted at layer 2. Your MacSEC is fully enabled, and this is kind of where we were trying to get to. So, I guess with this in mind, right, whenever you're trying to come up with a way of bypassing or attacking some kind of new technology, I think it's useful to kind of look at parallels, between whatever you're currently working with and similar technologies that have been compromised in the past or even recently. And with that in mind, this particular section, section 6.6 in the 802.1x 2010 standard kind of stuck out at me. And basically it's comparing, it's basically stating that conceptually the cryptographic capabilities provided by 802.1x 2010 kind of play the same role as similar cryptographic capabilities provided for wireless networks in 802.11, right? So I think what they're alluding to here are parallels between MacSEC and WPA. And actually, if you look at, why WPA1 was released back in 2003, well, when it was released, what it was introducing was layer 2 encryption between the access point to the station. And this, authentication that provided access to this encryption was provided by EAP or using pre-shared key as a fallback or alternative. When WPA was released, there was a major paradigm shift that had to happen, from an attacker's perspective, because, prior to WPA, injection-based attacks were all the rage. You could use them; they were very effective against web. They were very effective against open networks. But now, because of WPA, they're no longer possible due to that layer 2 encryption. So what you saw was a major shift in focus from attacking the encryption itself to actually attacking the authentication mechanism and not even dealing with the encryption. So that's where you start to see the WPA handshake captures and dictionary attacks against PSK networks, and that's when you start to see rogue AP attacks against weak EAP methods on wireless networks emerge as well. So if you fast forward to 2010, right, 802.1x 2010 has been released, and very similarly, we're providing hop-by-hop layer 2 encryption using MacSEC. And this encryption is either occurring between the device and the switch, or from 2 switches to kind of encrypt the traffic between the 2 of them. Once again, authentication is being provided by EAP or PSK as a fallback. Kind of see where I'm going with this. So, I mean, the obvious hypothesis here is that it makes sense to start with a hypothesis that you could also perform a similar shift of focus and start looking at attacking the authentication mechanism, rather than trying to attack MacSEC itself, because why do things that are hard? With PSK, I would venture to speculate that some kind of dictionary attack may be possible, although I haven't really worked on that, so I don't know. But in this talk, we're talking about attacks against weak EAP implementations, so another spoiler alert there. To kind of more understand these kind of parallels, let's talk very briefly about attacks against WPA2 EAP, right? And so the most commonly, widely known weak EAP method is EAP PEEP, and it's very similar to EAP TTLS. So you can kind of talk about them, in the same way. The way EAP PEEP works is that the supplicant, and remember we're talking in a wireless context now, the supplicant is going to make an authentication request to the authentication server, which is going to respond with an X509 certificate. At this point, basically the role of this certificate is for the authentication server to prove to the supplicant that it is who it says it is, that it can be trusted. The supplicant is either going to accept or deny, it's either going to accept or reject that certificate. If it accepts that certificate, it means that trust has been established between the supplicant and the authentication server, which moves us from the outer authentication process to the inner authentication process of EAP PEEP. And the inner authentication process happens when the secure tunnel is established between the supplicant and the authentication server, and basically transmit your identity, your username, password in the form of hashes, what have you, through the secure tunnel. And the secure tunnel is there to prevent you from sniffing this process passively. So this process does have security issues. Remember, we're operating wirelessly. Two researchers named Brad Antonowitz and Josh Wright, back in 2008, they were able to discover that you could use a rogue access point attack to force a supplicant to authenticate with a rogue authentication server. What do we mean by rogue access point attack? Well, basically, you have all these wireless devices here, and you force them to connect to your own access point, establishing a man in the middle. There are many ways to implement this, but that is the general concept that remains the same. So pretty much you force them to connect to you, and then you force it to authenticate with your rogue authentication server. And to do this, you have to send the target device, one of these X509 certificates, and it's probably going to have to be self-signed or at least generated by rogue CA, but in a lot of cases, the supplicant will either just automatically accept it, or it's going to be left up to the user to accept the certificate, in which case, you'll always find someone within an organization who's going to accept that thing. So it's kind of okay. Making this worse, right? When we talked about inner authentication as being the part that's happening through that secure tunnel. Well, the strongest form of EAP authentication available for EAP PEEP and EAP TTLS is MS-JAPI2, at least the ones that are widely used. So MS-JAPI2 is interesting because although it provides mutual authentication, it actually is vulnerable to a cryptographic weakness that was discovered by MacSEC Marlinspike and David Holton back in 2012. Essentially, once you capture the MS-JAPI2 challenge and response that is sent through the secure tunnel, using the rogue AP attack that we just described, you can reduce it to 56 bits of DES encryption using a divide and conquer attack, which, at that point, Marlinspike and Holton were able to demonstrate that with a 100% success rate, regardless of the length of the password, they were able to convert it into an NT password hash, which is password equivalent, within 24 hours with a 100% success rate. Now remember, this is back in 2012. Although they were using a $100,000 cracking rig to do this, if you look at what their cracking rig would cost now, it's somewhere between like $10,000 and $20,000, which is roughly within it's actually pretty much within the range of most kind of like mid-level, I guess like the startups of the criminal world, if you will, let alone in like a nation state or like an APT. So let's go back to 802.0x 2010. With all this in mind, the most important takeaway about 802.0x 2010 from an attacker's perspective is that it still uses EAP to authenticate devices to the network. And EAP, as we just talked about, is only as secure as the EAP method used. So, the 802.1x 2010 standard allows any EAP method so long as it supports mutual authentication, supports derivation of keys that are at least 128 bits in length, and generates an MSK of at least 64 octets. And there are plenty of commonly seen weak EAP methods that meet these requirements, including EAP PEEP, EAP TTLS, etc. I think you see where we're going with this. So this is where we kind of go into our new contribution. We're going to introduce something called a rogue gateway attack that can be used to defeat 802.1x 2010. This slide is kind of misleading because it's saying defeating MacSEC with using rogue gateway attacks. We're just avoiding having to deal with MacSEC by kind of cutting it off at the authentication process. So the goal of a rogue gateway attack is to force the supplicant to authenticate with the attacker's device. Remember, we're on a wired network, not a wireless network, so we're going to have to get creative in terms of figuring out how, a way that we can do this. Once you get this device to authenticate with you, you're able to capture hashes, which you crack, and then you get credentials, and you can authenticate directly with the network at that point. So when we talked about bypassing 802.1x 2004, we used a man-in-the-middle style bypass. So here you see we have this rogue device that's directly between the authenticator and the authorized workstation, which is the supplicant. We're going to have to do something a bit different with 802.1x 2010. We're going to have to go for direct access because this isn't going to work due to that layer 2 encryption. So let's talk about how we can build a device that can do this. The first step of actually setting up our bypass is actually just to set up our device. We see this is our rogue device here, kind of our design for it. we have our three network interfaces, the side channel interface, and that's going to provide us remote access to this device, via LTE or what have you, right? We're also going to have an upstream interface that's going to be connected, or eventually be connected, should I say, to the switch port. And we have our PHY interface here, which is going to be, or PHY, I don't actually know how to say that. I just see it in documents all the time. PHY, okay, cool. Learn a new thing every day. So we have our PHY interface, and that's connected to the supplicant. And the device itself, you just use a mini computer. We use an Intel NUC, running Fedora 28. So what we're going to need is a way of diverting traffic to the rogue device. So I'm going to take a look at this picture, right? This is a set of train tracks. And in the end of the train tracks here, we have this little train station here, and then we have a switch here, and depending on which way the switch is configured, if the switch is configured in mode A, the train is going to go directly into the train station. If the switch is configured in mode B, I just spoiled it, in mode B, the train is just going to bypass the station entirely. It'd be cool if we could do something like that with Ethernet, right? So you can buy these little devices off of Amazon for like $10, and it's a mechanical A-B splitter. You press the A button, and your Ethernet traffic is diverted mechanically through rogue A, or through port A. Press the B button, and it's diverted mechanically through port B. This would be cool, but since it's a leave-behind device, if we're going to actually use this, we need a way of manipulating that push switch. There are a couple ways you could do this. Theoretically, you could use a relay to do this, which essentially you either use high or low current to kind of like affect where the where the Ethernet traffic is going to go. Unless you're an electrical engineer, and that's definitely not me, building something like this is going to lead to impedance issues, which is why a better option is to use solenoids. A solenoid is basically a linear motor. You have a rod going through, that's with a coil wrapped around it, and you run electricity through the coil, and depending if it's configured as a push solenoid or pull solenoid, it's either going to result in that rod being kind of like slammed outward or pulled back in. So you can use that to create a pushing motion, which you can use to manipulate those buttons we saw there. So our completed rogue device design is going to look like that. We have a rogue device as set up as we saw before. We're also going to have these physical A/B splitters on either side, our upstream splitter and our downstream splitter. And we're going to have this wired link between the two of them. And we'll also have a passive tap that is going between these two splitters when it's in bypass mode that will allow us to inspect traffic. If you've ever used Michael Osman's throwing star land tap, you build something that's basically similar to that and use it to inspect traffic when you're in bypass mode. So when the switches are in mode A, traffic is completely bypassing the rogue device and going directly between the authenticator and the supplicant. When you use the solenoids to flip the switches into mode B, now traffic is diverted to the rogue device. So to actually implement the attack, we flip the switches, after we planted the device, we remotely flip the switches to mode B, and we shut down the upstream interface, which essentially blocks any traffic from being sent to or from the authenticator. And then we set up our rogue authentication server to listen on our PHY interface. And essentially what this does is it forces the supplicant to authenticate with us. And you'll have to inject an equal start frame to yourself to get this to work, and we'll talk about what that is later. But this will actually force the device to authenticate with you. And then once you are able to capture those hashes, provided they're using a weak EAP method, you can crack them, and then you bring down your PHY interface, bring up your upstream interface, and authenticate directly with the network. And you just kind of very lazily avoided having to deal with 802.1x entirely. So here's our updated demo. There's going to be some lag because I don't really know how to fast forward through it. But okay, so in the bottom right, yeah, so those are the solenoids actually flipping the A/B switch. I made them really big so you could see them, although obviously you'd want to use a smaller implementation. Actually, the first time I got this to work, I freaked the hell out of my wife because she's like, "What is that? Did you electrocute yourself?" And which I was actually pretty concerned about myself because I don't really do this very often. But yeah, so essentially we set it up. Is this paused? Yes, it is. Okay. So yeah, we diverted the traffic to us. It's playing again. I don't know how to control this device, I'm sorry. But what you will see soon is that basically, yeah, so we've cut off connectivity from there, and we have our hashes that we've captured. And from there, we go ahead and crack them. So, thanks. I honestly don't know why you're clapping. That is like the laziest attack that, like, whatever. They wanted me to come talk about it, so. So let's take a quick detour really fast. Now that we've gone over that, kind of some other stuff that I looked into while working on this project was kind of the current state of Mac filtering and Mac authentication bypass, because it's something that's been affecting me directly a lot lately. So fun fact, not all devices support 802.1x. Who'd have thought, right? But not all devices support 802.1x. But enterprise organizations, that need to use these devices, they still need to be able to deploy them anyways. So when this happens, when you're an enterprise organization that uses 802.1x, but you have to deploy a device that doesn't support it, traditionally what you've had to do is create what's known as a port security exception. And a port security exception, essentially you just disable 802.1x on the port used by that device. When you do this, you usually replace 802.1x with Mac filtering or some other weak form of access control. Not always, but usually. And historically, these have been pretty prevalent because of the widespread lack of 802.1x support by peripheral devices such as printers, IP cameras, all those essentials that, just don't have the sophistication of like a full workstation or something like that. So port security exceptions have traditionally been very low-hanging fruit for attackers. It's much easier to try to find a port security exception than to try to actually bypass 802.1x 2000 whatever, using a bridge or a hub. The problem is, and I kind of had to go try to verify this myself just by looking into things, because anybody do any red teamers here, or people who've done like physical security assessments? Yeah, haven't you gotten the impression that these are just becoming much and less prevalent? Like, it's just slowly kind of, yeah. Well, I mean, when you think about it a bit, it actually makes sense. If basically support for 802.1x peripheral, for 802.1x by peripheral device manufacturers, it actually has increased dramatically in recent years. A good example of this, if you go on Newegg or whatever and just look up multifunction printers and try to find ones that support 802.1x, pretty much every major manufacturer of a multifunction printer has at least one model that's affordable by an enterprise budget. And by that I don't mean like a $5,000 printer, I mean like, couple $100, that supports 802.1x. So the result of this is that as legacy hardware is phased out, either breaks or just gets cycled out, on a whatever basis, it's gonna, it gets replaced with 802.1x capable models. So what this means is that port security exceptions are becoming much less prevalent than they used to be. And although they're still there, they're not quite the low-hanging fruit that they once were. Which seems like a good thing, except for the fact that, we have to remember improved adoption of 802.1x does not necessarily imply strong port security for peripheral devices, for the following reasons. To begin with, 802.1x 2010 support is really only just starting to become a reality for really, really expensive enterprise networking hardware, let alone peripheral devices. Additionally, we mentioned that 802.1x 2004 can be bypassed using bridges, injections, etc. And we're releasing a tool that makes it really easy to do that as well, so that's going to become a little easier to do. With that said, adoption for secure EAP methods can be expected to be lower on these peripheral devices than on domain-joined devices. So it kind of begs the question, can we just attack EAP as a means of kind of compensating for the diminishing returns that we're getting from port security exceptions? And doing this actually makes sense when you consider that the adoption of secure EAP methods is already low across the board, let alone peripheral devices which often can't be configured from centrally in the same way that a domain-joined workstation can be. So I guess your first option for doing this, if the peripheral device is using something like EAP PEEP or EAP TTLS, you could use a similar rogue gateway attack like what we talked about before. You don't actually need the mechanical splitters to do this time though. You just set up your transparent bridge like we talked about, and then just disable your upstream interface, disable your bridge, and launch your rogue authentication server on your FI interface, right? And then from there you're able to capture hashes, crack them, and authenticate directly with the network. Interestingly enough though, honestly like one of the most widely used EAP methods that you see using peripheral devices such as multifunction printers is EAP MD5, which is really, really old and kind of crappy, but when you think about it, it's also really, really, really easy to set up and configure, and it's still better than Mac filtering, right? So, you can honestly, if you're deploying EAP MD5 and protecting all your printers with it, you can say, yes, all of our devices support 802.1x. We're not going to tell you how we implemented that, but they support 802.1x. So the way EAP MD5 works, once again, it's a really old EAP implementation. The first step of the EAP MD5 authentication process is that the authentication server is going to send an EAP request identity frame to the supplicant. And the supplicant is going to respond with an EAP response identity frame, which is it's providing a username. The authentication server is then going to create a randomly generated string of characters. Awesome, we're good. It's going to create a randomly generated string of characters in the form of an EAP challenge, and it's going to send that off to the supplicant as an EAP challenge request. The supplicant is then going to take that randomly generated string of characters, concatenate it with its username, concatenate that with its password, and then dump that through the MD5 hash function. And what comes out of that MD5 hash function is the EAP challenge response, which is sent back to the authentication server. The authentication server is then going to do the exact same hashing operation that the supplicant did, generate its own response, and then compare it to the one that it received from the supplicant. If they match, then authentication succeeds. If they fail, then authentication, or if they don't match, authentication fails. So, kind of the thing to remember about this authentication process is the entire process is occurring over plain text, which if you think about it, we don't have the benefit of that tunnel that we had with EPP or EPTTLS. And what that means is that an attacker can basically sniff this process passively, capture the username, capture the EAP MD5 challenge request and the EAP MD5 challenge response, and then basically perform a dictionary attack to obtain the password. And actually, a couple of researchers from China in 2012, they were able to recover EAP MD5 credentials even faster using a length recovery attack. So, I mean, this is essentially a really, really broken protocol. So, with this in mind, and leveraging what we know not only about how to attack EAP MD5, but how to attack 802.1x 2004 as well, it follows that we can start out by using a bridge-based approach, a bridge-based bypass to place a rogue device between the supplicant and the authenticator. We then start sniffing traffic being sent back and forth between these devices. We then wait for the supplicant to authenticate, sniff the EAP MD5 challenge, sniff the EAP MD5 response when it does, crack the credentials, and just then authenticate directly with the network. There is one major drawback to this approach, and that's that we have to wait for the supplicant to re-authenticate with the switch. Which actually that's not going to happen unless we disable a virtual network interface, or I'm sorry, disabling a virtual network interface isn't enough to make that happen, and it's realistically not going to happen unless we actually unplug the supplicant from the switch itself. We could use the mechanical splitters that we talked about with 802.1x 2010, but honestly the less overhead the better, and right now we're going for simpler. Basically another thing that the third contribution that we have here is the EAP MD5 forced re-authentication attack against 802.1x 2004. We mentioned that the first two steps of the initialization process, right, which realistically are the first two steps of the EAP authentication process, that's pretty much the whole thing combined, are that the supplicant is going to send the authenticator an equal start frame, and that's going to signal to the authenticator that it should send the supplicant an EAP request identity frame because we're beginning the authentication process. We also mentioned that this first step, the equal start frame, is optional. The reason why the first step is optional is that the authenticator needs a means of forcing the supplicant to re-authenticate, in the event of a problem, in the event that it needs to reconfigure something, etc. So that's left as an optional step. The problem with this is that the supplicant has no way of verifying if the incoming EAP request identity frame has been sent in response to an equal start. Essentially, like, we can force re-authentication by sending an equal start frame to the authenticator as if it came from the supplicant using MAC spoofing. And the result will be that the authenticator is going to send an EAP request identity frame to the actual supplicant and kickstart the re-authentication process. When this happens, both the authenticator and the supplicant are going to believe that the other party has initiated the re-authentication attempt. And as you can see here in this little video here, we can just repeatedly inject equal start frames using escapee in the bottom left, and that forces re-authentication. And it's very, very easy to do and very fast. So if we take this information and add it to our first attack, our passive attack against EAP MD5, we come out with I guess what we call the EAP MD5 force reauthentication attack, in which we start out by introducing this rogue device to the network directly between the authenticator and the supplicant, set up our bridge as before, start passively sniffing traffic. We then force reauthentication by sending a spoofed equal start frame to the authenticator. And then from there, that allows us to immediately capture the EAP MD5 challenge response and the EAP MD5 challenge, crack those, and then we can authenticate with the network that way. And this is pretty fast if you just run this. Yeah, we've literally just by running the thing, now we have the request ID, the challenge, the response, and also the identity. And that's it. I guess like the first proposed mitigation of this that comes to mind, although honestly this is probably not bulletproof either, is to put a safety bit in the EAP request identity frame. You can set it to 1 if the frame was sent in response to the equal start frame, and check it when the supplicant receives an EAP request identity frame. And essentially, if the safety bit's set to 1 and the supplicant did not recently issue an equal start frame, you abort the authentication process. So just to wrap this up, just to summarize our contributions, what we kind of went over today, we've introduced the rogue gateway and bait and switch, which in conjunction with one another can be used to bypass 802.1x 2010 by attacking its authentication mechanism. We've also introduced an updated and improved. We've also updated and improved existing 802.1x 2004 bypass techniques, emphasizing on the techniques introduced by Alva Duckwall back in 2011. And we've also introduced the EAP MD5 force reauthentication attack, which is an improved attack against EAP MD5 on wired networks. Some key takeaways before we wrap this up. Port security is still a very, very positive thing. Please keep using it. But it's not a substitute for a layered approach to network security. Deploying port security does not absolve you from very basic responsibilities like patch management, kind of keeping tabs of, it's part of, it needs to be part of a larger system that is designed to keep your network secure. And additionally, the benefits provided by 802.1x can be undermined due to the continued use of EAP as an authentication mechanism. And finally, improved 802.1x support by peripheral devices, or should I say peripheral device manufacturers, is largely undermined by lack of support for 802.1x 2010 and low adoption and support rates for strong EAP methods. If you want to look over this information in more detail, there's going to be a blog post. I tried putting in the entire URL of the blog post, but it just kind of took up the entire slide. So it's just the first results on digitalsilence.com/blog. And finally, we have if you actually want to try performing these, the tool and the associated documentation is available on github.com/solstice/silentbridge. Thank you very much.